seen it, though you won't believe it. It's a miracle year in which we're living. Come on outside, it's a beautiful day. A gentle breeze blows across the ocean, sending waves that crash upon the sand. Hey mister, did you watch Slow Down again? There is time for you to smell the flowers, even though the thorns get in the way. Hey mister, what's your theory for today? Ooh, I've seen it, though you won't believe it. It's a miracle year in which we're living. Come on outside, it's a beautiful day.
Oh, come on outside, ladies and gentlemen, boys and girls. What you're about to see is out of this world. Step right up now, don't be shy, because we're about to show you how cars can fly.
Here's a tale of a suburban housewife who dares to fight with the icon of his day, and she finds her own miracle on the way. I said, hey now, life's a joy. You gotta try your best and give your all, and when the facts don't fit the theory, change the facts again. Ooh, I've seen it, though you won't believe it. It's a miracle year in which we're living. Come on outside, it's a beautiful day. It's a beautiful day.
5, 4, 3, 2, 1. Silence.
Hey, sorry about the echo there. You know, this is the modern technology. But we are Saturday Science Chat, and we've got a great show today. You don't want to miss it. Yes, I am Dave D. Hilscher, and I'm your host today for a great show. Again, you don't want to miss it. It is with, in my opinion, the greatest geologist of all time, great friend too, and we are in a great time zone. He's all the way exactly on, I think he's exactly on the other side of the earth, at least time zone wise. But if you've tuned in for our Saturday morning chats, you've come to the right place. It's sponsored by the John Chappell Natural Philosophy Society. And in the beginning, I'm always like stuttering and finally get warmed up. I need to do like warm-ups or something. I'm also David D. Hilscher of Dissident Science channel, coming up to about 3,400 subscribers. I want to welcome all my subscribers. And of course, today we are going to be speaking a little bit before, after all, some announcements here and things. We're going to be speaking today with Dr. James Maxwell, and he is, I guess you could say he's the father of the word, at least, expansion tectonics. But he will be talking about his fifth in a series of talks with us called Blind Faith. Now, I can imagine what that means, but we will be talking with him shortly. But again, I want to thank everybody for tuning in. It is a really great pleasure to be able to do this show, because it is the only show of its kind in the world. No one else brings on people who are critical thinkers like this and treats them like real scientists doing real science. Of course, this is where you're going to find the future people who will be in the textbooks, in my opinion, because this is where you find science moving forward. And that's because people outside the mainstream are the ones who usually push science forward when we are stuck. And we certainly are stuck in plate tectonics and physics and cosmology. So I want to thank everyone from the John Chappell Natural Philosophy Society and the Dissident Science channels for tuning in today. Without you, this wouldn't happen. Of course, we are where critical thinkers meet. We're the John Chappell Natural Philosophy Society, named after John Chappell, who started this organization in the early 2000s. And of course, the CNPS uses the term natural philosophy in a broader sense, which includes physics, cosmology, mathematics, and philosophy. And our goal is to return to the basics where things really went wrong. And again, natural philosophy was the word before we had the word physics and cosmology. Our mission is to be an organization above all that promotes critical thinking without malice, to be an organization that supports, publishes, and promotes serious work outside the mainstream, and to provide a forum for open debate and modern topics in physics, cosmology, philosophy, mathematics, and geology. And to provide a forum for presenting serious papers and theories without fear of censorship, and to be run in its entirety by its members. Who we are? Well, we are open to challenging mainstream science. Of course, this should be the law of the way science works. But unfortunately, when you have institutions and institutions get money and people make money at institutions, they want to keep control of things, I guess. And unfortunately, our educational system doesn't really cater to critical thinking, which is sad. Well, at least not in physics, cosmology, geology, and a lot of other sciences. Some of them they do, but unfortunately, a lot of the, more mainstream subjects that have been around a long time are not that way. Of course, we encourage competing ideas or models, and that shouldn't happen, right? The universe is only one way. Well, we do allow for that, and we also follow the scientific method. People think, oh, hey, James Maxwell throws all the things out of geology and just does what he wants. No, folks, it doesn't work. I guess what I would say is, do you think we're stupid? I mean, no, we have to follow science like everybody else. In fact, that's why we have come up with different ideas, because we are following the scientific method and all are following the data out there. And instead of saying, oh, this is a problem and ignoring it, we confront it. And you'll meet somebody today who's done that quite spectacularly. We can also consider an idea without accepting it. That is, reserve your judgment. If you are a person who believes plate tectonics, that for some reason you believe that Pangaea existed and there was, for some reason or another, all the land on the earth decided to gather together on one side and leave one gigantic ocean, well, you can, but you should consider a different idea like expansion tectonics and give it a try. That's the right attitude. Of course, we give voice to the voiceless. Unfortunately, sadly, Dr. James Maxwell should be, the premier geologist today at whatever university, and should be doing quite well. But unfortunately, history has shown that changing people's ideas is not exactly always easy. And this is where science always advances outside the mainstream, as I said before. We are not. What are we not? We are not a specific point of view. That is, we are not. Some organizations are. For instance, the Electric Universe. They really subscribe much more to the electrical side of the way the universe works, and that's totally fine. Everybody's free to think what they think and propose what they want to propose, and I do herald and applaud anybody who is trying to come up with better models. Of course, we are not a general science organization, so you're not going to find us giving classes on thermodynamics. We have people talk about that, but we are not generally. We pretty much focus on physics, cosmology, mathematics, philosophy, geology. And then, of course, we are not a new age kind of deal where we talk about energy and the flow and all that stuff, sort of what we call science poetry. We're not talking about conspiracy or UFOs. Why do we not get into these areas? Well, we want to stick to the foundational science like light and gravity and fields and magnetism, tectonics, math, philosophy, Big Bang, cosmology. Things that are the basic stuff, like we talk about light, and light's really important, gravity, but we seem to not really know what those are despite what mainstream science says. We do have websites, so you want to check those out. Sciencewoke.org, online magazine for critical thinkers. Really great if you're not into the real technical side. That's a great place to start because it's got lots of great articles that are easy to read. And if you love science, and it also gives you the place where is science going wrong, because you're not going to find that almost anywhere on the internet. So that's a great resource. Of course, nationalphilosophy.org is where you can go and discuss things. Join in, register, and watch the conversations. There's always great conversations going on there. And if you want to check out our Wikipedia, we do have one, over 10,000 pages on there. You actually have, in my opinion, the best description in an encyclopedic form of expansion tectonics, and by who? Dr. James Maxlow. And that absolutely should be part of Wikipedia, but Wikipedia is the consensus of everything. And of course, the consensus is not going to accept new ideas. So anyways, check those out. And we are supported by our members. It costs us around a couple $1,000s a year just to do what you're seeing happening here. Our websites, our show that we have here. We have other things that we do and we subscribe to. So our websites do have subscriptions, and those subscriptions are both monthly and annual. We have a newsletter subscription and MailChimp. All of these things cost money. Like I said, over $2,000 a month. In fact, we just paid a bill last week for $300 for security of our server. What? Yeah, we get hacked. And we were getting hacked for over 5 years, and it was quite bad. You'd come to our website once in a while, it says, you have been taken down by Anonymous of Brazil. I lived in Brazil, so I guess somebody out there wanted to make that known. But now that does not happen because we pay a company to keep that from happening. And those kinds of things do cost, and we do have monthly and annual memberships, and you can make donations, and we get people doing all of those. I want to thank our monthly donators. $5 a month, that's about $60 a year, and that certainly helps, but other people have more means to help us out, and I want to thank. We get new memberships all the time, and it's certainly been very grateful. And of course, we do get donations, which really keeps a lot of this going, and I do want to thank our patrons, Dr. Cynthia Whitney, our chief scientist officer, Nick Percival, Duncan Shaw, an anonymous donor, my father, Kurt Renshaw, and many others. But these people have stepped up to the plate when we've needed money to keep this organization going, and it's greatly, greatly appreciated. And you can, of course, do that by going to our website. CNPS 2021. The official launches this month. I will be putting up a page. I've got to do that. I've been super busy with my own job. Yeah, I don't make a living at this. Nobody really does. But we'll be putting that out. And basically right now, if you're wanting to submit a paper, we will be having the papers. And in the fall, the format I think is going to be pretty simple. We're going to have people record their talks, and we'll have them on our website or on our YouTube channel. Well, we're going to put them all out at a certain time, and people will be able to watch those. And during the evenings, at least in the United States, will be in actually morning I plan to do 2 mornings on Saturday and Sunday, and then evenings during a couple days during the week. Or we may just do it over a number of weekends for a month, because if we do it that time, of course, we have a better chance of getting people from all around the world. 10 a.m. to noon is a good time for trying to get most everybody around the world, except for the east side of Australia. Those people would be, I think, from midnight to 2 in the morning, but the rest of the world would be good. But that's kind of what I'm thinking about right now, and so that will all be taken care of. But certainly we have people who do want to present. We have people with new books out there. And speaking of new books, we have Ready to Publish, Notfinity. We have the Ether book that is absolutely ready too. And we have our first reviewers have reviewed our book, and not reviewers, but basically readers, and made suggestions. We're writing a new intro to our book. We've changed the cover a little bit, etc. And those people who are waiting, I know we've got quite a few people waiting to read it to help us out with the readability. That will be coming up soon, but we are in the first kind of adjustment of the book. Very great suggestions by my friend Luis Sarbon from Brazil, an engineer who's presented particle models of light. That's why we're having him read it, because we're a particle model. So those things are look forward. And of course, if you have something you want to publish, we can help you with that. We're going to be using KDP, Kindle Digital Publishing from Amazon, and that allows you to do ebooks. And by the way, the author of the ether book, which is over 400 pages, yes, this is a particular ether theory, will be giving away the ebook for free. And I just got that notice. And he will be selling, of course, the book as well. And he says he's going to donate all the proceeds. He has been a great patron of this organization and as a scientist, but he remains anonymous under his request. So we do have people in our community, some community news. If you haven't checked it out, if you haven't checked out Fractal Woman Lori Gardee, she gave a paper, I think at the same conference that we had at the University of Vancouver, where our guest today spoke. And so she has one out on spin magnetic dipoles. So you want to check it out. I think this is wrong. Oh no, I don't know what, I'm not sure. Oh no, that's what it says there, but it's got a picture, and I don't know what this is. Maybe I saw it and then forget it. Anyways, go to Lori Gardee, Fractal Woman, and you will see spin magnetic dipole, and take a look at that. I feature people who put out videos. My dad's been just like pumping out videos. So if you haven't checked it out, linear polarized light, he talks about that. Actually, one of the great things about it, you don't have to subscribe to the particle model, but he does do a lot of research on looking at the history of these things. And of course, you may want to check that out. It's a really great video on a lot of topics you've been talking about, like the speed of electricity, the speed of light, the speed of gravity, those kinds of things. So you want to check out the Particle Guru and play the coming attractions, Dave. I'm glad I do this to myself. Coming April, this is it. I don't know what's wrong with the sound today. It isn't great. I know it, but what can you say? Anyways, let's go forward. You can't ever find. This is interesting. We've got somebody for next week already lined up. The threshold model, how quantum mechanics fails. Yes, folks. And if you want to see and talk with an experimentalist, this is a guy. There are a number of experimentalists. You should see the pictures. You don't believe me? Here's a picture of Eric's lab. Now, this is some serious equipment, and this is just his stuff. So he is a really excellent mind. He's one of those, I would say, amazing, crazy minds in science that really think outside the box, and crazy in an absolutely great way. I really enjoy his work. Look at that. There's a roll of toilet paper with all this stuff. You can tell he is absolutely thinks outside of the box and really has no problem of actually setting up his own experiments. That is quite amazing. Also, will be coming up a sort of a departure from the normal topics that we have. And that departure will be talking with Dennis McCarthy, who just happens to be a proponent of expansion tectonics. In fact, if you look about 5 years ago and look us up, I think on the CMPS website, I think on our CMPS channel, you can look them up. If you look up at MPA or CMPS and Dennis McCarthy, he gave a talk on flora and fauna. He has a really great talk where he talks about how animals and flowers, that flora and fauna that are on very remote Pacific islands way across the Pacific are only found in two places, like on this island and on the west coast of the Americas. And of course, that is amazing. How would that be? Especially he focused on animals and plants that could not travel. That is, the plants, if they hit salt water, would die, even their seeds, and also the animals, they couldn't fly, they couldn't be carried. The only explanation is, well, if you look at the time where they meet up, is where when the Earth was smaller. And he had a really great talk. I'm going to try to get him to do that talk again now that we have a new audience up. That's definitely worth checking out. But he is also doing work on using AI to look at just gajillions amounts of text and to find out that that Shakespeare really got a lot of his work from Thomas North, and there's a lot of evidence for it. And it's just going to be another way of looking at a critical thinker in another area. We do that off getting this idea from Dr. Eberly Spencer, who had been president of this organization for many years, who would often bring in people from very different points of view just to get people's minds in the critical thinking mood in a different direction. And I think that'll be good. So I've asked Dennis, and he's going to be happy to present this, and I think that'll be a lot of fun. Of course, I've been talking not weekly, but at least once a month with Stephen Bryant, and he is definitely going to be talking about his book, Disruptive. He's got things going on in his own life right now, very busy, but he is looking very much forward. You're going to really enjoy that. I've been announcing this every week, but you do want to stay tuned. If you haven't got the book, take the book, buy the book. I'm not sure if it's a Kindle. I think it's probably available in e-format, and take a look at it. But we will be having him on. He'll be talking about his work. Of course, we have the finite theory coming up. I'm going to talk with Phil. We got to get a date set up for that. We've been announcing that for a while, but he has his own theory as well. And again, if you have something you want to talk about, and that's a lot of our new topics that we have been putting on here. Last week we had the scalar theory of everything with John Hodge, and it was quite interesting. A really great work. You're going to always learn something from somebody else's theory, because they are thinking about the universe in a very different way that you have, and it will definitely spark your imagination and really get you thinking, because a lot of this stuff is really, really good, and you're thinking, that is interesting, and it'll make you change your mind. So those people who will say, there's only one model of the universe, you got to be careful, because like even in our model, my father and I have our model of the universe, and if it wasn't for all these other people's and other people's models and people's work, we stand on the shoulders of everybody else. So I want to check that out. So we're almost there, folks. Play the bumper for today. I know our guest is smiling there on that last photo. It was one of the greatest conferences for me of all time, because I got to meet one of my heroes, and that is the person today. Got to meet him and actually drink a pint, I guess they would call it. But before we do talk to him, I just want to make sure you know who he is. That's Dr. James Maxwell. He's a retired professional geologist who worked in a mining and exploration geologist through much of Australia. And look at that. What's this thing here there? Oops. And see, I should not click around. And the good thing is, this is live, so we can mess around. I was trying to get rid of this link in the middle here. But again, he worked in mining exploration most of his life in Australia. So he was a person out there in the field. During that time, he returned to Curtin University of Technology in Perth, Western Australia, to study and research expansion tectonics. And from this research, he gained a Master of Science degree in 1995, followed by a PhD in 2002. Of course, he famously was contacted by one of the most famous geologists of the modern age, Samuel Warren, and he was asked to take over his work on what James Maxlow coined expansion tectonics, or expanding Earth, Samuel Warren Carey, you gotta get that right, and he wrote in 1994 a letter I think you can see that on the websites for that James has, and basically said, you take this over. And boy, did he take it over, doing, in my opinion, probably writing the most important book and the most amazing work in all of the history of geology, which is Beyond Plate Tectonics. Yes, I have my copy. It's on my shelf, always in the back. In my opinion, it's I'll read a little bit about that. Plate Tectonics signposts that this is something more advanced than basic academic courses might cover, while the subtitle of Unsettling Science confirms our suspicions. The new whole book is all revolutionary and new, unsettling to anyone who thinks there will be no major revisions in the earth sciences. I mean, folks, this is the biggest understatement in earth sciences that I think it was ever uttered. It is just as stimulating to those people who understand that scientific stuff will never be finished. Of course, that is. So I highly recommended this book. I think it's the most important book in geology ever written. And it has the work of what should have been hundreds of people, but it was done by one man. And of course, I think we're done. Yep, there we are. So I want to remove this, and I want to bring up our guest here, James. I will unmute you. Hello, James, and welcome back to our time zones that are not clashing anymore. How are you?
Yes. Hi, David. Yes, very well, thanks. Yes, I'm glad to be back in the moderately good time zone instead of starting at midnight at 11 o'clock, whatever it was.
That's right.
Yeah.
I think are you in your 70s now?
Yes, early.
Early. Oh, early. The early period. You can tell you're a geologist. You said you're very careful. There's the early, mid, and late. You were in the early primeval 70s era, whatever you want to say.
That'd be the Paleo 70s, the Paleo 70s, not the Meso or the Neo.
But I want to welcome you. And so you're going to be talking today about what you call blind faith. And why don't we get your screen sharing while I talk here. So as James...
I'll just butt in. I changed the title a little bit.
Oh,
the context is exactly the same, but I just changed the title to be more consistent with the previous podcasts that I've done, and also consistent with more podcasts I've got coming.
Okay.
So it's not much different, but I'll show you. So I'm sharing now. Share screen.
Okay, let's make sure we see it. Once I see it, I'll put us up there.
And this one. Share.
Okay. All righty. I'm starting to see. There we go. All right. Once you get your first slide up, so once you do that, I'll put you.
That is a picture of a Western Australian, what's called a Western Australian Christmas bush. It's a beautiful. It's a parasite. It actually lives on trees. It's like a mistletoe.
You're kidding. It looks like, but it looks like it's underwater.
No. That's the blue sky.
Holy cow. And all we hear about in the United States is how there's all these dangerous animals in Australia. And man, it's so beautiful. And I think part of it's because of the isolation from expansion tectonics, sort of isolating this sort of smaller continent in the sense of it's not, the big mega continents like that. And I think that's one of the reasons you get this incredibly different flora and fauna. So very beautiful.
You won't get that up there. All right.
Let's see if you get your PowerPoint up there.
Yeah.
And I will remove myself and everybody, James Maxlow.
Hello, everyone, and welcome to my podcast. As mentioned, I've changed the title a little bit. I call it The Age of Plate Tectonics is Drawing to a Close. And this was to reflect, as I said, this is to reflect on my previous podcast to keep it consistent. In this podcast, which is in addition to my earlier podcasts on expansion tectonics, sets out to establish a prima-firma case against established plate tectonics by questioning the very essence of plate theory, whereby Earth radius is constrained to a constant radius over time, and to question why this premise still has not been tested using modern geology-based global observational data. During the 1950s, Emeritus Professor Sam Warren Carey of the University of Tasmania set about assembling the ancient Pangaean supercontinent on a present-day Earth model in order to quantify continental drift theory. In his modelling studies, Carey went to great pains to ensure that he compared and assembled the shapes and sizes of the continental blocks accurately on a 60-centimetre diameter model of the Earth. In his paper, he commented that the reward for this zeal for accuracy was frustration, but in the end, the rigorous approach paid off, for it revealed a discrepancy which had not been apparent. It was not my method that was at fault, but my assumption that the Earth of Pangaea was the same size as the Earth of today. This, in essence, was Carey's aha moment when he realised that the physical crustal data was telling him something completely different to accepted plate or continental drift theory. From this research, he went on to conclude that the assembly of Pangaea is not possible on the Earth of the present radius. Unfortunately, with the subsequent acceptance and promotion of plate tectonic theory, these very important physical observations and conclusions of Carey continue to be totally ignored to this day, preferring instead to resort to cartoon reconstructions of the supercontinents as per the 2017 assemblage shown on screen in a minute. Down. Sorry, I'm having trouble moving that screen. There we go. Ignoring Carey's scientific modelling studies in preference to plate tectonics theory is therefore a blatant disregard for factual science. Because of this disregard for factual science, plate tectonics has now reached the point of cult status, drawn in by blind faith in the hundreds of millions of research dollars spent annually. And it would seem that no amount of factual observation will convince plate tectonists otherwise. In this vein, I will now make an important prediction. The age of cartoon-based plate tectonics is drawing to a close, and the age of expansion tectonics is dawning. Unbeknownst to most people, conventional plate tectonic theory is governed by the most fundamental of assumptions, which insists that Earth radius, and hence its mass and surface area, have remained constant or near constant since the Earth was first formed. 60 years ago, science was perfectly justified in rejecting the then expanding Earth theory in favour of the New Age constant Earth radius plate tectonic theory. The reason why this constant Earth radius theory was adopted during the mid-1960s was because, having just convinced science that continents could indeed move over time, it was a quantum leap in faith to then expect these scientists to further contemplate that Earth radius could also increase over time. Hence, scientists rejected an increasing radius Earth scenario and instead erred towards simply trusting their gut instinct rather than resorting to good science, as Carey did, and forever after have assumed that Earth radius has been constant over time. By constraining Earth radius to a constant value, the unforeseen outcome of this assumption is that all subsequent assumptions, models, research, and theses based on evidence gathered about the Earth are also constrained to a constant radius Earth model. If this most fundamental assumption about Earth radius is shown to be wrong, then it stands to reason that all subsequent models and theories must also be wrong, and hence plate tectonics is also wrong. Since plate tectonic theory was first introduced during the mid-1960s, a vast amount of modern global observational data have been gathered and accumulated about the Earth, and as students, interested persons, or scientists alike, our task in life is to record and interpret this data in an unbiased professional manner. This modern global observational data is factual evidence and ranges from tectonic data gathered by each of the geosciences through to data about the oceans, biological sciences, atmospheric and climate-related sciences, space-based science, and so on. The point being made here is that utilisation of this data, in particular the mathematical-based data, is unconsciously constrained to a constant Earth radius premise. At no point has anyone looked outside the constant radius Earth paradox to allow or encourage this data to tell its own story. For example, a typical Pangaean supercontinental assemblage using modern seafloor crustal mapping by Smith et al. 1994 is shown at left at the same scale as the present-day Earth. Where the dark grey areas, these ones shown here, represent known remnant Jurassic seafloor crusts. In order to maintain a constant radius Earth premise, the surrounding white areas had to be invented by tectonists to account for inferred pre-existing crusts. On a modern-day Earth, these white seafloor crusts do not exist, and on a plate tectonic model, are required to have been subducted and recycled back into the mantle during the past 200 million years or so. This plate tectonic continental and pre-existing seafloor crustal plate assemblage is based on the strict assumption that the radius of the Earth, and hence its surface area, have remained constant throughout time. From this assumption and accompanying ad hoc theories, we are then told that past assemblages of continental crustal fragments are a random, non-predictable, and cyclical process of plate collision, assemblage, breakup, and dispersal. Herein begs the most fundamental of tests which modern science is reluctant to carry out, let alone recognise. If these random continental crustals fail to reassemble precisely to enclose the entire Earth on a smaller radius Earth model, then plate tectonics must be correct. However, if these continental crustal fragments do reassemble on a smaller radius Earth model to completely cover the entire ancient Earth, then plate tectonics must be wrong. I encourage you to think about this. In contrast to the previous plate tectonic model, the expansion tectonic Pangean model shown at right was constructed by simply removing the constant radius Earth insistence and allowing modern published seafloor geological mapping data to constrain and assemble all plates back to the early Triassic. On the expansion tectonic assemblage shown, all continental crustal plates assemble precisely to enclose the entire ancient Earth with continental crust. Hence, plate tectonics must indeed be wrong. On this model, there is no requirement for random, non-predictable crustal assemblages, nor for the presence of pre-existing seafloor crusts, subduction, or arbitrary fragmentation of the continental crusts. In contrast, it has been shown in my previous podcasts that, contrary to random, non-predictable crustal assemblages, all continental and seafloor crustal plates reassemble precisely with a better than 99% plate fit on smaller radius Earth models. These small Earth assemblages will be shown shortly to be a predictable and evolutionary process involving an exponential increase in Earth's surface area and radius over time. This simple test alone, using modern continental and seafloor geological mapping, published well after plate tectonics was formally introduced, tells us that there is something seriously amiss with plate tectonics, which must be further investigated. It is now well known that the Earth's surface comprises a series of 7 or 8 major and many minor plates, made up of both continental and seafloor crusts. This data, as first introduced in the mid-1960s, is accepted as fact and is not contradicted or contravened by anything presented in this podcast. However, it is how this data is interpreted and used that matters. In an attempt to quantify the adopted premise that Earth radius has remained constant over time, McElhaney and Brock carried out an extensive survey of ancient magnetic pole data measurements, spanning East and West Africa during 1975. From these measurements and calculations, Macalini and Brock concluded that there has been no significant change in the ancient radius of the Earth with time. From this simple conclusion, paleomagneticians effectively took control of plate tectonics at the expense of geology-based sciences. And the science of apparent polar wander is now heavily relied upon to drive past plate assemblage studies. Paleomagnetics is now considered the cornerstone of plate tectonic studies at the expense of all other sciences. Meanwhile, an extensive program of seafloor magnetic and bathymetric mapping, accompanied by age dating, was being carried out throughout all of the oceans during the 1950s to late 1980s. This program was designed to quantify the established distribution of crustal plates and hence further quantify plate tectonics. The geological map of the world, shown here, was first published by the Commission for the Geological Map of the World and UNESCO in 1990. The colours shown on this map represent what I call time-dependent geology, where the coloured seafloor stripes, for example, represent the preserved growth history of each of the modern plates as volcanic lava is progressively intruded along each of the mid-ocean ridge spreading zones, much like the growth rings of a tree. On this map, the ages of each coloured seafloor stripe coincide with the major geological epochs and periods, extending from the youngest pink Pleistocene stripe, located along the mid-ocean ridges, through to the oldest blue Jurassic stripes, generally located adjacent to the continents. What this mapping means is that the yellow seafloor stripes, for example, located between the younger red stripes and the older orange stripes, represent volcanic lava that was progressively intruded along the ancient mid-ocean ridge spreading zones during the Miocene epoch, extending in time from 5.3 to 23 million years ago. During that time, the younger red and pink volcanic rocks, respectively, did not exist. During the Miocene, the two adjoining yellow stripes were then joined together throughout all of the oceans and remained united along their common mid-ocean ridges during this interval of time, progressively widening over time. Similarly, the colours within each of the continents represent rocks that were formed during the major geological periods and eras and coincide with the distribution of the ancient cratons, origins, and basins. It is unfortunate that at no point do plate tectonists use this mapping data to constrain plate assemblage on a constant radius Earth model, relying instead on their paleomagnetic apparent polar wander data. Why is this so? Because the mapping simply doesn't quantify plate assemblage on a constant radius Earth model, and hence it is quietly ignored. It wasn't until 1993 that space geodetists had enough observational platforms available throughout the world to attempt to establish a global network calculation, and hence determine a potential rate of change in Earth radius. It is significant to note that when Robordo and Harrison first established a global geodetic network in 1993, their global network calculations gave a root mean squared value of up-down, or variation in Earth radius, motions of over 18 millimeters per year. In other words, the Earth was found to be potentially increasing radius by up to 18 millimeters per year. This space geodetic network is like a glorified land survey of your property, whereby any misclosure in survey measurements is considered an error, and hence must be statistically meaned out to zero. Over subsequent years, this is precisely what geodesists have done. They have constrained their raw data to a constant radius Earth in order to satisfy the requirements of a constant radius Earth plate tectonic model. End of story. Nobody disputes the validity of space geodetic observational data. Of significance to this story is that in year 2000, 4 identical Cluster 2 satellites were launched by the European Space Agency. These satellites were launched to study the impact of the sun's activity on the near-Earth space environment by flying in formation to gather data around the Earth. For the first time in space history, this mission was able to collect three-dimensional information about how the solar wind interacts with the magnetosphere, how it affects near-Earth space, and how our giant spherical magnet called Earth reacts with the charged particles within the solar wind. This new information and related discoveries were considered by the European Space Agency's project scientists to be of great importance because they showed how the Earth's magnetosphere can be readily penetrated by solar particles. The Earth's magnetosphere is now shown to be full of trapped plasma, comprising charged electron and proton particles, originating from the solar wind as it passes the Earth. This flow of plasma into the magnetosphere increases with increasing solar wind density and speed, as well as increases in turbulence in the solar wind. In addition to penetrating the magnetosphere, it was also shown that the plasma travels down along the Earth's magnetic field lines within the auroral zones, entering the Earth at each of the poles, shown here. This European study suggested to the scientists that penetration of plasma may be a lot more common than was previously known, and possibly represents a means for the constant flow of charged electrons and protons into the Earth. The most important question that should then come to mind is, what happens to these electrons and protons, the very building blocks of all matter in the universe, when they enter the Earth? The answer to this question is that they must increase the mass and radius of the Earth over time, which, of course, is precisely what is required on an expansion tectonic Earth, but is contrary to the insistence of plate tectonics, and hence this observational data is also ignored. In discussing these important events, it is important to appreciate that modern global observational data can very basically be classified into geography-based data and geophysical, geodetic-based data. Geological and geographical data is pure observational data about rocks and landforms, whereas geophysics and geodetics requires mathematics in order to derive an outcome. In all cases, plate tectonists rely on the mathematical outcomes of geophysics and geodetics in order to substantiate their insistence on a constant radius Earth premise. At no stage is geology or geography used to substantiate this premise. This physical data is instead constrained to a constant radius plate tectonic Earth model. This is a shame because geology and geography represent a preserved record of the history of the Earth. It is not something that should or can be manipulated. If the geology and geography do not match the mathematics-based sciences, then it is the maths that is wrong, not the geology or geography. As just mentioned, of significance to this discussion is that modern satellite observational data gathering demonstrate that large quantities of electrons and protons are shown to be entering Earth and potentially increasing the mass and radius of the Earth over time, as required by expansion tectonics. So, it is now time to reflect on plate tectonics and see if it is not better suited to an increasing radius Earth scenario. Let us now digress and consider what if Earth radius truly is increasing over time. Shown here in spherical format is the geological map of the world as first published in 1990. As previously mentioned, the coloured seafloor stripes represent intruded time-dependent volcanic rocks. Logic dictates that when moving back in time, each stripe must be removed in turn and the continents moved closer together. In this animation, the globe will rotate a few times before removing each coloured stripe in succession, simulating moving back in time. As most of us know, when moving back in time, plate tectonics traditionally closes off the Atlantic Ocean and moves the adjoining continents closer together at the expense of the remaining oceans, in particular the Pacific Ocean. What I've done in this animation is to simply remove each coloured stripe in turn on a constant radius Earth model. without forcing the plate data into a preconceived Atlantic Ocean assemblage. By doing this, the bedrock geological mapping shows that each of the other oceans can just as easily be closed off, and each adjoining continent can also just as easily be moved closer together. To me, this new mapping provides strong evidence to show that all of the oceans progressively close, and hence all continents move closer together when moving back in time, but not in the random process that we're currently led to believe. From this observation, I pose a number of simple questions for you to ponder over. Now that we have seafloor bedrock mapping at our disposal, are we still justified in ignoring this mapping data? And should we still insist that only the Atlantic Ocean be closed to assemble the ancient Pangaean supercontinent? In this next animation, I am going to show you what happens when we move back in time and progressively return the volcanic lava represented by each of the coloured seafloor stripes back to the mantle from where it came from. What I do is simply remove each coloured stripe in turn and reduce the radius of the ancient Earth in accordance with the surface area data to assemble all plates back together on a smaller radius Earth model. The yellow circle shown represents the outline of the present-day Earth. What this animation demonstrates is that by progressively reducing the radius and surface area of the Earth when moving back in time, all remaining plates assemble together with an overall plate fit estimated to be better than 99% fit, without the need to arbitrarily fragment continental crusts, to dispose of any existing crust by subduction, or to invent pre-existing crusts in order to maintain a constant radius Earth premise. In this animation, by the early Triassic period, all coloured seafloor volcanic rocks have been returned to the mantle. Marginal marine sedimentary basins, shown as white, here for example, then merge to form a global network of basins coinciding with continental sedimentary basins. It is concluded from this animation that this unique plate fit and assemblage on a smaller radius Earth cannot be mere coincidence. By continuing to model geology back in time to the late Permian period, about 250 million years ago, on this model, all young seafloor volcanic crust, plus most of the marine sediments deposited along the continental shelves, have been removed. The distribution of published ancient continental seas are also shown in blue, and the modern continental outlines are highlighted as black dashed lines. As distinct from conventional practice, what is shown on this model is that all continental crusts unite precisely with a single unique plate fit to form a global Pangean supercontinent during the late Permian period, at around 50% of the present Earth radius. Each of the remaining small Earth models also show that large Panthalassa, Tethys, and Iapetus oceans are not required during model construction. These oceans are instead replaced by lesser continental Panthalassa, Iapetus, and Tethys seas, which represent precursors of the modern Pacific and Atlantic oceans, as well as ancient sedimentary basins located on many of the present-day continents. On these previous models, the transition from ancient seas to modern oceans only came about when the Pangean supercontinent, shown here, first started to rupture and break up to form the modern continents and intervening modern oceans. It is envisaged that breakup then initiated draining of waters from the ancient continental seas into the newly opening modern oceans, plus expulsion of new waters from along the newly formed mid-ocean reed spreading zones. The preliminary conclusions drawn from these increasing radius small Earth models is that there is no requirement for random, non-predictable, multiple plate fit assemblage options or ill-defined plate histories, nor is there a requirement for extensive, largely hypothetical ancient oceans to comply with the constant surface area premise, or for the fragmentation of any of the modern continents to comply with paleomagnetic apparent polar water studies. Instead, it is shown that the ancient continental crusts tightly wrap around and fully enclose an ancient smaller radius Earth. As mentioned previously, this ability to reassemble the continents precisely on a smaller radius Earth therefore confirms that plate tectonics is wrong. To add further insult to plate tectonics, we will now investigate what continental crusts have to say. During older pre-Permian times, continental crust covered the entire Earth, and exposed supercontinental lands were defined by a superimposed network of continental seas coinciding with a network of sedimentary basins. These seas are not shown on this animation. Construction of small Earth models back to the early Archean involves a radical approach to reverse engineering geology back in time. This approach focuses primarily on the established network of continental sedimentary basins surrounding each of the more ancient cratonic and orogenic crusts, shown here as red and khaki-coloured crusts. Modelling back in time involves the progressive removal of all young continental basin sediments and intruded magmatic rocks, and simply returning these rocks to the ancient lands or back to the mantle where they came from. Each continental basin and igneous complex is then restored to a pre-extension or pre-intrusion configuration on a smaller radius Earth model. By moving back in time, the adjacent margins of each sedimentary basin or igneous complex are then progressively moved closer together while still preserving the spatial integrity of adjacent, more ancient cratonic and orogenic crusts. When moving forward in time, all crustal elements making up the ancient supercontinents and seas are then shown to retain an intimate relationship throughout history. This intimate relationship lasted until crustal breakup was initiated during the late Permian, approximately 250 million years ago, and the modern oceans then began to open. From this continental crustal small Earth modelling study, it is shown that the origin and changing configuration of the supercontinents during these times involved a progressive evolutionary crustal process during a prolonged period of crustal stretching, along with changes to both surface area and surface curvature through time. It should be noted that this modelling study has never been contemplated before, other than what is shown here. However, as you can appreciate, this is not the problem that people see when trying to accept an increasing radius Earth scenario. The fundamental problem that scientists and the general public continue to have is comprehending where did the huge volume of material make out the seafloor crusts and underlying mantle go to when moving back in time in order to reassemble the continents. And more importantly, where does this huge volume of material come from when moving forward in time? Modern space exploration and near-Earth data gathering presents a viable causal mechanism for this increase in Earth radius and mass. From modern space-based observations, it is speculated that charged electron and proton particulate matter, originating from the Sun via the solar wind, accumulate and recombine to form new matter at the Earth's core mantle boundary. It is envisaged that this increasing new matter gives rise to mantle swell, which is then manifested at surface as crustal extension, currently occurring with all of the modern oceans along the mid-ocean ridge spreading zones. It is important to appreciate that, while speculative, this area of investigation is new science which hasn't been given due consideration as to what happens to these electrons and protons when they enter the Earth. It also provides a viable explanation for increasing Earth mass and radius over time, something which was not available prior to these modern space exploration discoveries. So, including this podcast, I have alerted you to a major contentious issue with regard to the continued support and reverence of the so-called modern plate tectonic theory. This theory continues to be extensively promoted in science to explain a diverse range of observed global observation data, and the theory is widely accepted by both scientists and the general public alike. Yet the very essence of this theory is based on a tenuous assumption that Earth radius has remained essentially constant throughout time. It is unfortunate that modern mathematical-based observational data gathering so firmly constrains plate tectonic thinking that scientists are now oblivious to any suggestion that there are viable alternatives to interpretation of this data. I reiterate that plate tectonics has now reached the point of being a blind faith, cult science, which demands absolute faith in their constant radius Earth premise. To me, even blind Freddy can see that the modern global observational data, in particular the geological and geographical data, is telling a completely different story to what we are currently led to believe. So it is well and truly time to review, revise, or relinquish the stranglehold that maths-based science has on tectonics, and to allow geology and geography to tell its own story. So thank you for your interest in expansion tectonics, and for those seeking more information, please visit my website or contact me at my email address shown on screen. Thank you.
My mic is muted. But thank you so much. I got a lot of people had questions, but you actually answered them as the talk went on, which was really good. But
I hope it didn't sound like I was losing my voice there, because I was.
oh no, gee, you're fantastic. You should listen to me. I'm hacking and my mind moves faster than my mouth, which I'm not sure is good or bad. And so I have a tendency never to finish a sentence. So when I'm on air, I try to, finish a sentence. But some really amazing things that people were noting. One of the first comments in our comment area was, 4 billion, I love your work, but 4 billion years? Come on. And I think one of the most absolutely amazing things that you have done. I mean, well, I mean, this is just me looking at it fact. You've done enough that you've probably, unfortunately, occupied 100 PhD theses that people could have written, but you did all the work already. But one of them is
nobody else would do it for me.
Yeah. But one of them is obviously, and that was one of the first things I saw with you. And I because you, even in the expansion tectonics world, right, you have people recreating the Earth back to when everything closed down. You look on Neil Adams' video, for instance, it's all when it's closed down. And it's very dramatic to see. It really teaches a lot of people, the light bulb goes on. That's what happened with me to see that. But then I saw your models and I go, hold on, you're going way before that. How did you do that? And I think one of them.
That's a good point, David. I'll just interject.
Yes.
Most models reconstruct the ancient seas back in time, and that's relatively easy, as Adams did with his brilliant modeling. But it only represents 4% of Earth history, and the problem is, well, that's easy. Adams is a comic artist or something or other, and Klaus Vogel from Germany was a civil engineer, and there's been others who are relatively nobody from the streets coming in and being able to create these things. But to take it that next 96% further back in time requires to be a geologist. You need to understand what the rocks are telling you and how to treat the rocks and dispose of the rocks properly over time, which is where I came into it.
Yeah, and this is, I'm going to show you. I'm going to take you off camera. It's going to go to me here, but this is a model that I asked James to make for me a model, and this is so nice. And one of the things that you see right away, let's take a look at Africa there. Africa's right there. This is what James is talking about. If you look at this, most of the people who are working with expansion tectonics don't have all those colors. And I was looking at, what are all these colors? What do they mean? And what you did was basically, as a geologist, are these ages?
Yes, they are.
Okay.
Yes, they are.
So you said to your, and I want to ask you one question. When did you see this? Because I don't know, was this from the beginning when you thought of it, or?
I was very fortunate in that I started this research in the early 90s, and coincidentally, this particular map was published in 1990. So I was very fortunate in being able to get hold of a map which contained the complete geology of the Earth in both oceans and continents. If you just hold that up again, David, and turn it round so you've got the Americas pointing to me.
Okay, America's pointing to you. It's better for me to look at it because this is a complicated one here. Okay.
Okay. So we're just getting there. Yeah. Now,
you want both of them? You want South America too?
No, that's fine. Just
okay.
People will look. Just hold it steady, David.
Okay. Well, sure.
See the pink area in Canada and North America area. They're the most ancient rocks in North America. So you can and Australia and Africa and various other countries have exactly the same ancient, what are called cratons and origins. These are rocks older than 2.5 billion years old. And these can be likened, if you can just imagine those as being like the continents.
Right.
So they're remnant ancient continents. Yes, Australia is ones in the west and in the north and south
you can
central.
see them in the west. Where you are, there is some really ancient.
That's right. So you can imagine these as being most ancient continents. So you take away all of the ocean crusts, as we did, and then all of the present day continents wrapped together to merge to that model that the 50% model. Then if you take all those the younger sedimentary basins away, which are equivalent to the oceans, they were the ancient seas. So they're the areas where sediments were being poured in from the exposed lands and covering up the ancient seafloor. So you remove those and the sediments go back on top of those most ancient crusts. And geology tells us that the exposure of those most ancient crusts, at least 10 to 40 kilometers of material has been eroded away from the top of those crusts. That has all gone sideways to form your sedimentary basins. So when you move back in time, you have to reverse everything and move everything back up onto the crusts. And then by reducing the size of the Earth even smaller, each of those most ancient continental fragments all fit together. Now, this should be impossible, but it's not.
How did you do? Okay, wait. It blows my mind just that you did this, and like I said, you, in my opinion, no one's done this much work ever in geology, in the history of geology and humankind. But how did you visualize this? I'm a visual person, right? I mean, one of the things people have no idea how hard it is just to make a model or just to even digitally, any of this. This is a huge amount of work. How did you go about it? Because you can see it, right? But how did you do it? Did you first do it on paper and then sort of get in your mind pieces of the Earth? I mean, how did you do that? I mean, you didn't get out your Google map expanding Earth, which I'm trying to get going. I have some ideas about how we can do that, but you didn't do that. How did you do it?
Well, actually, on these particular models, the base map that is shown on the front cover of my book there that you've got there beside you, if you just hold that up again. So that image on the bottom, that's my base map. So if you print that out and cut each of those what are called gores out, you can glue them onto a model, and that's precisely how I built that model for you, David.
Right.
So by moving back in time,
you can see it. See the lines there, people.
Yeah.
You can see those white lines.
The join lines.
Yeah.
So it was. Once I got those continents assembled at 50%. Then it was a trial and error piecemeal. So I knew by that stage of the research, I knew that the sedimentary basins formed a network. surrounding each of these most ancient cratons and origins. So, and by definition, sedimentary basins form by extension in the crust. So all the sediments are then washed into those low-lying areas. So by reversing the process, they all come together. And ultimately, we'll get this right, ultimately we'll go this way, the continents all come together like so, the ancient continents. So you remove all the sediments and they all fit together like that. That's fairly simplistic, but I had to do it piecemeal. So I just had to progressively reduce the size of the globes and progressively take away stuff until I got to that point way back in time in the Archean.
How many years did that take you?
It took 18 months. Each of those models took 2 weeks to make.
Okay.
And then I had to digitally process them, and it was a good 18 months to 2 years just making models of my research project. Yeah. So that were the second models of, in my master's, I had a different set of models, which, so these ones are
truly amazing. And that comes from, again, that question. It's really amazing how people, when they come across your work, have the same questions. And that's one of the first ones, like, holy cow. I believe you. I mean, I love Maxwell. See if I can find that here. The person's. Let's see. I'm pretty sure I can find that comment here. Let's see. Expand tectonic, appear to be growing. And well, I'll find it. Maybe my father is watching, but there's one about I believe Maxlow, but 4 billion years. Now, here's another question, all related to this whole thing. Antarctica. So you're talking about the United States or North America, right? And it's got a little bit of pink. You got Western Australia, a little bit of pink, which is the really, really old crustal surface.
That's right.
And then I'm watching your models go back in time. And you must like Antarctica a lot. Now, is that because, how do we know what Antarctica's surface is? It's all covered in ice. Do we have
all around edges? Pretty well all around the edges, there's exposed Archean crust, except for West Antarctica, the little one on the side. There's a lot of young Proterozoic, which is to Paleozoic sediments in there, which are younger. So I've got to get this right because it's always opposite of what you think. West Africa to Australia is actually on the east, and East Africa is on the west. But anyway, so East Africa, the main part, that was all the way around the edges and little bits in the middle, is exposed Archean crust. So I was able to just make a prediction that was most ancient Archean crust. And so I was able to retain that in each of the models as I progressively went forward, and it didn't contradict it. So I was quite happy to accept that that's all most ancient Archean crust.
There, my father's found it. It's from Brett. He says, I like this guy, but 4 billion years? Really? That was a great comment.
I have to own up here. That model is actually at around 1.6 billion years. Okay. But the difference from there to 4 billion, the increase in radius was only less than 10 microns per year.
Right. I mean, it was absolutely infinitesimally small.
From that, the 2/3 of Earth's history, which that one model represents, the radius increased by only 60 kilometers. And so I could make an identical model to that and call it Archean. So I'd have two models there. So I didn't. It was just called that one model Archean to Mesoproterozoic, which is the middle Proterozoic era, 14, 15 billion years ago.
Right. Well, I'm glad my father found that. Yeah, but I mean, that is quite amazing. So yeah, I was wondering about the Antarctica part because I thought you were really being, how do you say, you had an Antarctica fetish and you were just, that stayed around. So, but that's quite, so basically what you're saying is, even though we don't know underneath, what you're saying, the edge of that is all ancient.
Yeah. And Greenland's is the same.
And it turns... That's interesting. Now, yeah, that is weird because you've got Greenland and Antarctica having the most ancient crust, and they're both covered in ice, and they both go way, way back. And what you're saying, though, is that when you were doing the reconstruction, from what I understand, is that it turned out that it continued to work. It wasn't like you were getting contradictions.
No, that's right.
So that is totally amazing. That is really amazing. Now, the other one too, which is sort of related, I'm going to get to some questions in a minute, so I'll have my dad bring some of those up. But let's get just a few minutes here, Dad. Some other things: the oceans versus the seas. Right now, that's another interesting thing I saw during the Pangaea. If you were to look, and I was looking very closely at the maps now that I can read Maxlow's models better. Is that I noticed there was like an ancient sea that sort of covered the coast area of Canada and the northern America. So it looked like I saw a pretty big sea there.
That's right.
I just happened to see that because I know the area. But obviously, you are also then taking into account geology that people have said that, yeah, there's a shoreline here at this time. Did you do that?
Right. No, that's all published stuff. I just recreated those shorelines on my models.
That's all you did. Just that, right? Oh, gee, I mean, I will say
it was interesting because the published data just covers the continental areas. So there's a wriggly shoreline goes across a continent and out in the oceans. So so on a plate tectonic Earth, it's just higgledy-piggledy here, there, and everywhere. So you've got to make assumptions about what's actually happening. In my models, this bit of continent here matches that bit of continent over there, and this bit of continental margins, seafloor margins, matches this one here. So it all fitted together. It was just like, happened.
Right.
So
right,
I'm very pleased. Right. A lot of that data, I'm exceptionally pleased with the way all of the data, which, by the way, will be the theme of a number of new podcasts I'm building at the moment. I'll cover related data that I use to supplement this research. So I'll bring that to your forum.
Absolutely. Absolutely. My goal is to try to record as much as, people's work that need to be recorded so that we have it in, having videos. One of the things that I remember when we're going to get this question there. Well, we had a question up there. Can you put that question back? There you go. We'll get to that question. But one of the things that I was really happy to see is I saw finally somebody, I think it was Tasmanian, University in Tasmania, basically put up a older video of Samuel Warren Carey. We just don't have, video evidence or, people live recordings of people talking some of these great scientists. And one of the things that's great now is we can do that. So even though you're not doing lecture series and winning Nobel Prizes, we got you at least in recording history so that once people realize this is right, they're going to be able to see you talking about it. And I think that's just fantastic. Here's a question, Dryas. Have you considered the Earth was even smaller and mid-crust expansion and evident indicating a yet smaller original mass? So what they're asking is exactly what you're saying. It changes by microns, but are you, I know one of the things that's really interesting, I think related to this question, is you talked about how you think the moon was formed, and it has a lot to do then with a sort of different, it's not so much expansion tectonics. So is it the case that before this very, very small Earth, that maybe other things were really happening, that it didn't start out as a snowball in space and eventually accumulated mass? No. So is that the answer? The answer really relies in a sort of a different process. The expansion only really started at a certain time.
Well, as I mentioned before, that for 2/3 of Earth history, the increase in radius was only microns per year. Increasing by the mid-Proterozoic 1,600 million years ago, it was still only about from memory, about 10 microns increase per year. It's now 22 millimeters.
Right.
So from that point, there was a steady to rapid exponential increase in radius. So while looking at that Archean to Proterozoic model, that youngest model there, it looks like you could reduce it even smaller, but I opted to stay there because for crusts to form, you have to have a precursor. It's like a toffee bar. If you stretch a toffee bar with a center in it, you can stretch this far type thing, and before it snaps, or you break up in contents. But moving back in time, it'll come together. So all this bit of goo and stuff, toffee and stuff in the middle, must come back. So, but you can only get it back to a certain stage, and so that's at about the stage I've got with the model there. But getting back to what you mentioned about the moon, and I mentioned that in a previous podcast, where the size of that small Earth moon is the same size as Earth is the same size as the moon is now, and my age dating only goes back to 4 billion years. Whereas age dating of the moon takes it back to 4.54 billion years.
Right.
We don't see those ages on Earth. However, having said that, recent ages now take it back to a little over 4 billion years. So, and also the rocks, those rocks that's on that most ancient, the Archean model, they're all granites and volcanic rocks. Granites, volcanic rocks, and metamorphic rocks, which require a lot of heat. They're formed because they are molten. They're originally molten. So when all these most ancient crusts, continental crusts, come together, they're all made up of high temperature granites and volcanics and metamorphic rocks. So I think and I maintain that the reason why we only see rocks dating back to 4 billion years is because prior to that they were molten, and you can't date molten rocks. The moment that rock cools and crystallizes, and if it's preserved through to the present day, then you can date it, but you can't date molten rocks prior to that.
Right.
Whereas the moon. In my previous podcast, I indicated that the Earth and Moon were once one body, and it's subsequently destabilized and separated. And the Moon took all of the most primitive crust, the crust of rocks, and left behind the primitive mantle and core that now forms the Earth, and a little bit of the most ancient crust. So what you get is volcanic rocks, mainly volcanic rocks on the Moon, and by separating and cooling quickly, so they've cooled 500 million years before the Earth started cooling. So that's why you get a difference in ages between the Earth and the Moon.
Do you think that we're getting another question down here? Don't take that down, Dad. Do you think that because speaking as a geologist, that if it's true, because obviously this is a theory, right, what you're talking about, and that is that there was a separation and that the Moon took the most ancient crust. Do you think that process left behind a geology that made then the Earth have all of its forms that it has? Because if it would have stayed with that crust, would we have not had the sort of life and all the things that had gone on, or would that have not changed in your opinion?
Possibly.
Yeah.
The difference between the Earth and the Moon is while we have a lot of ancient volcanic rocks on the continental crusts, we also have a lot of granite, and there's not a lot of granite on the Moon. And granite, in theory, is a differentiation of volcanic rocks in the mantle region. So, so how that process operates, I'm not too sure.
Can't you answer everything? I mean, you've only answered 100 PhD worth of work,
right.
but we want at
I
least
have
5 more.
I have absolutely no idea what this question means or
Oh,
saying.
okay. So is the absorption proportion? I, I guess what they're saying is it's mass
Oh, the
versus
absorption
size.
proportional, not proportional to the
Yeah,
gain in
right.
mass. Well,
Proportional. Yeah, yeah. We have people
yeah,
that are not all English speakers, so
yeah. Well, it must be identical. What
okay.
comes in increases your mass, and
Okay.
yeah,
Okay. Okay. We did have a question from the, I'm going to show this. I got it from the green room. That is, the people who are sitting in the green room have the ability to come on and talk with you. But somebody did have this question. Has anyone used this model for modeling the evolution of our solar system? Since the mass of the Earth is changing, the orbit would be changing, assuming the mass of the other planets changing. I noticed I know you've talked about the possibility that the United States, the Earth would turn into perhaps a gaseous giant eventually. So do you think that, for instance, the big gas planets were once not gas planets and had gone through a similar mass increase?
it appears to be so. The thing with the giant planets is they're all strongly to very strongly magnetic, whereas the inner rocky planets are not next or near enough to be non-magnetic. The Earth is in a transitional phase. It is strongly magnetic. So where the giant planets and the Earth are attracting these plasma particles, these charged particles from the solar wind. So they're naturally increasing in mass. It's just that the giant planets probably started off larger than the Earth anyway. So they're absorbing a lot more, and also and I think Jupiter's got I think it's 20,000 times the strength of the Earth or something.
Right,
from
it is.
my head, something like that. So yeah, it's absorbing quite a lot of stuff. But and the other difference is the Earth is what I call a wet planet, i.e., it's got water, fluid, and gases. Just like the giant planets, whereas the inner rocky planets don't have these gaseous elements. So we may be in a transitional phase, and I think I mentioned in a previous podcast that within the next 500 million years, the rate the Earth is increasing in radius, will be the size of the giant planets in 500 million years' time.
Wow.
So hence, and of course, all this volatile elements are coming from the mantle. So there's more to come, and we're coming from the mantle, but it's also coming from the sun, of course, into the mantle.
Right. I mean, you've mentioned that numerous times that you mentioned in your talk today. Here's another question: doesn't granite only form in the presence of water,
No.
or otherwise it would be basalt? Is it correct? No. Okay.
Granite is granite because it has quartz, felspar, and mica is the basis of granites. These are the lighter elements called felsic elements. It's a felsic rock, whereas basalts are a mafic rock. They're rich in iron and magnesium, two totally different rocks. But granite can differentiate from the basalts and the other mafic rocks which make up the mantle. These can differentiate. It's like how can you explain it? Something you're cooking on the stove, and over time things percolate out and leaves a scum on the surface. It's like oil and water type thing. So they can differentiate over time. I'll make another point too, which I'll just digress slightly. The seafloor crusts are formed by intrusion of these mafic volcanic rocks along the mid-ocean ridges, and these mafic rocks originate from the mantle. So when you think about it, the seafloor crusts are exposed and quenched mantle. A lot of people don't realize and appreciate that, but that's their exposed mantle and are completely different to continental rocks. That's why when you move back in time to to 50% of the radius of now, you get all the continental crustal rocks merging together. That's then becomes like a shell, like the skin of an apple or shell of an egg. And by rupturing that and moving forward in time, it's the eggshell or apple skin is retained in these continental fragments, and you expose the yolk and whatnot, called the mantle, from in between those continental crusts. Just thought I'd digress on that.
No problem. We have time, which is good. We still have a half an hour. We do. If you are in the green room and you do want to speak with live with Dr. James Maxlow, please let me know if they're brave enough to do that. But I
haven't got one.
Oh yeah, what? Oh, this hat, physics police. Well, I had this whole concept of physics police and actually all kinds of creative things with it. But I sort of like it. It's easy. You know what's really funny? I've worn this out in public, and it's really weird because I'll be walking in a grocery store, right? And like shopping, whatever, and I'll come around a corner, and people will see the hat. It looks sort of like they see the word police, and all of a sudden they start to
excuse me,
yeah, it's like, oh, they don't see the physics part, they just see the police, and then they look at it and they're trying to figure out, is that a real police department? Of course, the United States has way too many police in general, but if people are interested, I just like it. It's sort of a easy idea, meaning, hey, we're not going to just take it. We're gonna police these physicists or scientists. It just turns out that way. But yeah, we can get those somewhere. But you actually, the way I made it was I went to one of those cap shops here in Boca, and you go to the mall, and you can make all these lids and everything. I think it's called lids, and you can put whatever you want on it. So I've made some for myself, my dad, and that kind of thing. So yeah, you can actually do that. Go to a lid store and have it. I got a certain type of font on it, so it looks like the police in the black and all that stuff. But another interesting something that you brought up, and you talked about it, and I'm not sure I necessarily agree with you, but I'm not, it's no big criticism. It's just maybe because I've dealt with people from, not only you're dealing with people who go or in the plate tectonics world versus, expansion tectonics, we deal with, people who still cling to the Big Bang and relativity, things that just don't work. But you were talking about, of course, you said blind faith, but you were saying you're changing that to it's really the last hurrah for plate tectonics, which I agree. I really do think that more and more people are embracing this. I'm finding this even in our group. People are skeptical these days what they read on anything, because we're getting fooled by so many people in power that I think people are now putting their skeptics hats on more. And when they look at it, they really do. In fact, I think we're getting more and more people coming this way. But one of the things I'm thinking is that you had mentioned that
people you mentioned expanding Earth or expansion tectonics,
right?
Geologists and whatnot, and they just shut down. They just don't want to hear about it. I had a young Canadian female geologist working for me when I was working with Newcrest a few years ago, and she studied at Cambridge, and of course studied plate tectonics. And my son happened to go out with her. They became friends, intimate friends, and he's passionate about my research, my son, and he tried to loan this young lady a copy of my book, but she just went, no, I just don't want to know about it. And this is exactly what you get with John Eichler and I. John took me to his university in Little Rock to meet one of the geology professors, and he just went, hey, I don't want that. We gave him a book, and I don't want that book. We insisted, but yeah, they just don't want to know about it. And
but another thing, I think another thing you're saying, and it's very similar, I think, and that is, it may be a pattern of when things die out, right? for instance, in my movie Einstein Wrong, started in 2005, and I gave my mom this assignment to call 50 universities and ask if anybody wanted to talk about relativity and defend it, because she said, look, I'm doing an Einstein Wrong movie. Would you come on? It turns out she got one person to talk. But the truth of the matter is, she said, and it's very true, she couldn't find a person who was a specialty or made a living off of relativity. There's really only one person I really know, and that's Kip Thorne. And he is an old guy. I mean, he's got to be in his 90s now, and he's from Caltech. And he sort of has ridden that wave sort of in the mid part of the 20th century. But if it's the case that relativity, and I think there's a similarity here with plate tectonics, if you just bear with me a little bit, it's the case that when something not only isn't it, I mean, it's being touted as this is the answer. Relativity is everywhere. Without the universe, relativity doesn't work. That's what they say. Even though GPS scientists say you can't use it, doesn't work. That's what they say. But with time, people realize it, and this sort of like holding your hands back is sort of like an admission that it's dying out. That is, you can't go to a university. When my mom would call, they go, oh, well, so-and-so is a professor. He's mostly deals with the gravitation and that kind of stuff. He does a little bit of relativity, but let me think. There isn't anybody. And the reason is, if it was useful, you'd have a heck of a lot of people doing it. If it's really totally doesn't do anything for mankind like relativity, you have it the case where no one's getting a degree in it. I mean, our chief scientist from MIT, she's in her 80s now. She got her degree in the late 60s in special relativity. The first application, it failed. So maybe it's the same thing that's going on plate tectonics. Because you had mentioned something to me that was kind of shocking, is that you see plate tectonics, you hear about it, but you said there's not a whole lot of people really in it. It's more like a side group that's sort of interested in it. Maybe you could explain the lay of the land, because I think it's happening the same thing in plate tectonics. It just doesn't work, and that it's slowly just dying out. Is that true? It's
just unfortunate that we just can't get papers published. If I put a paper into a respected a journal of whatever, they'll immediately assign that to a couple of peer reviewers. And I go, and of course these peer reviewers, they're not expansion tectonics. So they are plate tectonics. They're actually reviewing my paper in relation to plate tectonics. And of course they reject it.
Right.
And then it goes back to the editor, and he rejects it because the peer reviewers have rejected it.
Right.
And I maintain there is only one peer reviewer that's capable of peer reviewing my papers, and that's me.
That's true.
Because I'm the only one.
Well, I think there's other people we could volunteer. I mean, you made it.
There's a handful of us. Worldwide.
No, but what I'm saying is, though, you had mentioned to me, let me go to a university, a great university in Australia for geology. How many people today are spending their time working on the shifting and movement of the plates? I don't think almost anybody's doing that anymore.
I was a professional geologist for 40 years, and in that time, I never once needed or used plate tectonics in any of my exploration or mining geology. And you can ask any geologist in the world the same thing, and they'll say, no, it has no relevance to me. It is purely academic.
That's so funny, because that's exactly the same thing that happens with relativity. I remember someone talking at the MPA, I think it was in Albuquerque, and my friend Greg Volk, he said, oh, Dave, I was sitting in the audience when someone was talking about how GPS doesn't, relativity is wrong, and GPS only goes against it. It shows evidence against it. And Greg said he was sitting next to a guy who was in GPS, but he wasn't giving a talk because he doesn't want to go public. But he turns to Greg and he goes, Greg, I just want to let you know, I'm in GPS. We don't use relativity. And so what you have all these evangelists out there, what I call science evangelists, like Neil deGrasse Tyson. The one I saw, Bill Nye the Science Guy. My daughter went nuts when she found out I actually met Bill Nye the Science Guy, because she was watch all the videos when she was in elementary school, learning all about science with Bill Nye, who was this fun guy. Well, he gets up there, holds up his cell phone, and goes, "Okay, here's this phone. If it wasn't for special and general," he actually said that, "your GPS and phone wouldn't work." And I had to bite my tongue because my company had sent me there, and I didn't want to say, "That's not true. I know a guy who has over 30 patents in GPS what will dispute they don't use it." Yet the repeating of it, the repeating of it, the repeating of it. But what's happening is they don't use it, and you can't find people. So is that true? You mentioned a profession that sort of still clings to it in geology, that's maybe more theoretical.
It's just taught as a unit in the undergraduate geology.
So
they have to know. They have to know about it.
So there's nobody so if I go into geology today, I go to the best geology school in Australia, and I will not mention I know the greatest geologists of all time, because they'll say, "Oh, you mean Samuel Warren Carey?" I go, "No." But anyways, if I were to go in there and I say, who's your plate tectonicist and can I get a degree in that? Does that still happen? I don't think it does happen anymore.
It's just a minor unit in geology. You've got sedimentology, you've got petrology, you've got structural geology, you've got engineering geology, you've got mineralogy and all that sort of stuff. They're all subunits within that degree. And that is only one part of it. And even I've actually never been taught plate tectonics, because my original degree in the early
that's 70s, your problem. There you go. You weren't indoctrinated. Shame on you. That's we now find the real truth.
They were just mulling over Continental Drift in the early 70s. So, and then I graduated, and then I went to work. When I came back in early 90s to Curtin University, by that stage I'd made up my own mind, and actually it wasn't taught then either. I did one undergraduate just to refresh my degree, that I did honours, masters and PhD, and it was not touched on at all.
No, so but how did you get your degree? If didn't you write your degree in expansion tectonics?
Yeah.
But how did that happen? What did you go to, like a ballet school and find the one geologist there who doesn't care? I mean, how did you do that? No, I'm kidding, obviously.
Yeah, no, I self-funded, of course, but I was fortunate in that certainly for my PhD, my supervisor was a student of Sam Carey from University of Tasmania. And my early supervisor in my master's was also a student at University of Tasmania. So they were sympathetic. And I was also fortunate that the head of the Department of Geology was also sympathetic to what I was trying to do. And so they allowed me to do it. But I just did my own thing.
Wow, that was so lucky. I mean, seriously. Otherwise, you'd have to get a PhD in, like, the history of Finnish clitics of the 14th century.
You can do a PhD on anything,
Wow. I know, but I mean, you have to
specialize. You can major in whatever you want.
So somebody was saying,
there was a young bloke went through with me. He was doing research on a lithium mine in the Pilbara region in the north, and he spent a total of 7 years virtually peering down a microscope and doing all sorts of fancy analytical stuff for his degree. But he specialised in this suite of minerals from this particular mine in the Pilbara. So yeah, how relevant it is to anything else, I have no idea. But he certainly knew how to then take it a step further and use it for other things.
So one of the things that is somewhat sad is that you don't have students in a university who are studying you, who then write PhDs standing on your shoulders and getting that work out there. Is there anything like that happening with you? Do you
No,
get any contacts with anybody?
no. It's an interesting thing. When I was doing masters, that's right. I was this same supervisor that I had for my the PhD. He got me to I'm having a seniors moment here. Tutor students in mapping, in photo mapping. And I think I've lost my train of thought here because I'm not too sure why I'm telling you this.
I
So
was
just
talking about students that were following. That
oh
could
yes,
follow you.
oh yes, that's right. It wasn't him. It was my actual supervisor that I had. He was telling me that as for second year geology, structural geology is one of the units you do. He gave there was an assignment. Gave an assignment for these students to compare and contrast plate tectonics and expanding Earth theories. And of course, there's no right answer, of course. It's a compare and contrast. You're writing a compare and contrast paper, so there's no answers. You can come up with whatever answer you want. But anyway, the students didn't take it that way. They all thought they have to get the right answer. And the right answer, of course, is plate tectonics. Wow. So therefore, they all rubbed expanding Earth in the dirt and promoted plate tectonics. So this influenced their mindset from then on, that expanding Earth expansion tectonics is pseudoscience. I had another interesting incident. At that time, I had two supervisors, one from the Curtin University, or Curtin University of Technology, and the University of Western Australia. And the head of the department, who was my supervisor from UWA, was also a student of Sam Carey. And he, when he was teaching, he had one little unit in his whatever course he was doing with the students on expanding Earth, which I thought was really good. And he got me to come in and give a talk to these students, and brought my early models in, and I gave a talk to them, and they were all, oh, wow, they were all gobsmacked that this could possibly be feasible. Anyway, I think it was the following year. I thought nothing of it. The following year, I was in the library, at the university library at UWA, and a young fella came past and goes, "Oh, hi, James. How you going?" And I go, "Who are you?" "Oh, I was in that talk you gave me on expanding Earth." So I was rather chuffed with that. So at least somebody, if you allow these students to be open-minded about these things, they will absorb it. Yeah. But it's not happening anymore. That fellow has since died, and the other fellow, my other supervisor, has also since died. So they're gone.
That's amazing. Well, it's interesting because somebody similar in a similar situation about teaching both sides of the story and becoming a critical thinker. My friend Luis Sarabom from Brazil, he's an engineering teacher, but he would give topics. And he was very much a student of physics and the problems in physics, right? Like, the wave particle duality and not having really a model for light. We talk about it, light's this and light's that. We have no idea, mainstream science. So he would, for instance, say, here's a topics that you can choose. And in science, I want you to write a general paper on it and report back. That's going to be part of your grade. So he did this for many years. It'll take one, like the Big Bang. He told this story to me. We talked at length many times. And he said, okay, student, his rule was, okay, you're going to look at these subjects. And he already had it sort of already lined up. He knew that these subjects had a strong, arguments against the Big Bang, relativity, I don't know if he did Plate Tectonics. I'm not sure he did that one, but other topics, the expanding universe, those kinds of things. And the student was not given a good grade if they came back and said, well, of course the Big Bang's right. Any idea against that's wrong. They had to come and say and basically demonstrate that they were going to look at both sides, like you would be in a lawyer. If you were in a lawyer and you were in a class, a lot of classes, you have to look at both sides. It doesn't matter whether or not you think this person is innocent. We've got 1,000 videos of this person killing them. What would be the arguments? And that's what you're trying to do. You're trying to develop critical thought. So he did that, and the students would come back, and he did that for many years. Well, I called him up. This was a while back, maybe 5 years ago. And I said, I really like to get you to maybe even talk about how you do this, how you set it up, because other teachers could do this. Here's his story. Very similar. He goes, here's what happened. A third of my students really loved this. Their minds were opened up. They just said, wow, I never knew relativity had problems. I never knew the Big Bang was so problematic. Their eyes opened up, right? Like this one student you met in the library. He says another third didn't really care. They weren't moved one way or another. They did their job. They looked at the things, arguments for and against the Big Bang, for instance, and they wrote them down. They got a passing grade, but they didn't care. The other third were going to his not managers, but his bosses or people who are above him. And after a few years, they're going, we've got this guy who's making students write about how the Big Bang's wrong. And so a third of them were turning this guy in. So if you looked at that, a third of the students were curious minds, critical thinkers, really thinking on their own. A third didn't care. And then a third were like, I follow this. And it's sort of like, if you even look at monkeys, probably, you would probably find this distribution of the way certain monkeys will try new things and other monkeys, nope, you got to do it this way. Other monkeys, I don't care, do it this way, they'll follow. It seems to be a part of the animal that we are to have these different traits. And sadly, he had to give it up. He couldn't do it anymore, and he loses his job. Now, I think maybe it's going to be the case that perhaps, was it autodidact or something like that is the name of people who are, it's a word in linguistic, it's a word in the dictionary that means a self-taught person. That is, I am not a geologist. I am not, and like you said, you are a geologist that was able to take the part where Neil Adams couldn't go is beyond that, because you're a geologist. Neil Adams not a geologist. I'm not a geologist, but we have enough logical thought, and if we are students, I'm a student of yours. When I write in my emails, as your student, I am, and I think there's going to be a point at which that people are going to know enough about that and see enough about it. I mean, there's millions of views of Adam's, video, that eventually somebody somewhere and some young people are going to start to embrace this somewhere. And there's going to be a critical mass to which all of a sudden the students aren't going to be that way, because they're not going to be indoctrinated. Maybe plate tectonics has died out so much no one cares, no one uses it, and this other idea is so beautiful. Maybe that's what'll happen. Maybe it has to happen from the public. I think I wrote a paper that happened with relativity. I believe the reason Einstein was so famous, I think, wasn't because he wrote, did special relativity, and as you go closer, all this stuff. I think it came from when he came up with something that was so amazing and obvious to the general person that it really clicked with, and that is, there's light and there's gravity and they're related. And the average person could understand that. They could understand in their mind, here's gravity, here's light, it bends. Whoa, that is cool. And that took off, and the people understood that. Maybe with plate, expansion tectonics, that maybe that's where it's going to happen. It may just not happen in the universities. I don't know. But anyways, let's see. One other question I have. Anybody in the green room? I think people we're getting near the end here. We got 10 minutes left. If you do have a question, put we are watching the. Let's see. Oh, let's see. Is Ben? Oh, here we go. This is a fun one. I like to put ones up here that are nice. It says Dr. Maxlow's is Ben Franklin smart? Just saying. So yeah, and somebody says I agree. So that's good. Well, that means that people, I have found here. I'll give you an example. Even in our group, James, when we first there were people talking about expansion tectonics before I knew you in the MPA, and people were sort of ignoring it too, like Now, I don't know. Do you know Dr. Alexander Unsker? He is the one who wrote the Higgs fake, who blew the lid off.
Was he at the
No, he was no. He actually is a person who wrote several books. One called the Higgs fake, and the Higgs fake was exposing how the particle physicists pretend to find stuff and their scientific method, which is horrific. If the people from NASA or SpaceX were to walk into the Large Hadron Collider in Europe and sort of watch their methods, they would in 5 minutes look at them and say, you guys are all nuts because there's no logic going on. Well, he exposed that. And he is one of the people that is closer to, Einstein, and because he's from Germany, etc. But he said to me the other day, because of he watches these videos, he goes, one of the things I'm really getting interested in is expansion tectonics. Now, this is a person who actually gives lectures around Europe talking about things that go against particle physics, and he's a doctor of physics in Germany. And so one of the things is, as you gain these people one by one, you get more and more people, so that within our group now, it's almost given. If you have a theory of the universe, a model of the universe, you better explain mass increase. That's it. It's not something that you can argue against in some sense. So I think what I see people doing, and it's the same happening with like plant-based diets. I've been on one for 8 years. I reversed my heart disease, all this kind of thing. My company now is realizing that. I'm giving talks. I have friends who reverse their diabetes, all that kind of stuff. But what's happening from 7 or 8 years ago, I had no support, never heard about it. You're starting to hear more about it because it really works. So what I think's happening and what's good about you coming out and doing these things is slowly they hear it over and over. It's a lot. Can you imagine? Okay, you got to imagine, James, if someone reads your book or looks at this and they go 4 billion years, they just got over the shock that the Earth's expanding. You're standing on a ball that's expanding. And now the guy comes and says, oh, well, I can go back 4 billion. What? It's overwhelming. And I think part of this, like this, is that you get from people who want to look into, maybe should look into it.
So these podcasts, David, that you're doing, they're putting out on YouTube or something, aren't they?
Yeah, of course.
Yeah. Because I'm working on a series of additional podcasts. I've got one on paleomagnetics coming up. I've got one on ancient magnetics, ancient climate.
Cool.
Biogeography, which is plant and animal distribution.
Right.
What's the other one? Fossils and all sorts of things like that. So I've got a series of them coming, probably 4 or 5, or maybe even 6, working on them. We've got 2 more ready to go. But yeah, there will be a series to supplement what I've already done.
Yeah. What you have to do is
it's based on what I've written on my book.
Right.
I'll just pull out those pictures and that.
But see, here's what happens. This is the way the world works now, James. People are riding in their cars. So they're going to, they listen to my daughter doesn't watch TV. She doesn't watch TV. She gets all of her information through people who talk about things she likes. And what happens is people get these little bits. And so we're going in YouTube and you find something interesting, you start subscribing, those things come up. We tag everything in this. So we make sure your name's here, expansion tectonics here, all the things in. What happens is when people search plate tectonics, I put plate tectonics in every video you have. Because if you search on plate tectonics, you're going to get something like this come up.
Yeah.
and people get shocked. I've seen it happen over and over. And what you want to do is now take what's in your book and make them into these nice
That's what I'm doing.
bite-sized
Yeah.
chunks.
Yeah.
Because when a person's sitting in an airport and they have nothing to do and they're science fans, they're looking at the science guy and all these things, and they come across this and it blows their mind. We slowly change the culture, but that's the way it works now.
That's
It just
right.
works that way.
Hopefully, yes.
Yeah. Okay. Here's a question. It'll be our last one. And this is just a huge question, but maybe we'll stop with this. What's the future of expansion tectonics?
Well, hopefully it will take over from plate tectonics, because that's the direction I'm focused in, is to, like plate tectonics did for continental drift, something modern data came into being and they were able to reinterpret this data. Now I've taken that original data a lot further, much further, because there's been an exponential increase in global data availability of global data, and even media and computer technologies to be able to process this data. This data was not available when plate tectonics was first formulated in the mid 60s. It's like, I always think in 1968, my father gave me a slide rule. That was the state of the art.
Yeah, I know. My dad had one too.
I was
remember.
very proud of my slide rule.
He told me. He taught me to teach that. Yeah.
So here's mid 60s. The technology was just archaic compared with what we have now. So all I'm doing is expansion tectonics is taking this modern global observational data, and I don't know if you picked up on the acronym there, DOD, God.
Yeah, sure. Yeah. Just happens to be that way.
Global observational data, and allowing the data to tell its own story, rather than force it into an archaic model perceived in the mid 60s.
Well, you said, I mean, one of the things is if you just look at it, and that's what, if people take the time to look at it, I always say to people, if you take the time to look at it, you cannot come to any other conclusion other than the Earth has been expanded. It's impossible. You have to close your eyes. You have to do this, right? Like those people. You got to do this. Like, I don't want to see it because it's going to have to change. And I think that's the other part too, where this comes from. Dr. Carey, my mentor, who showed special relativity wrong. He's a PhD in physics in the 1940s. He talked to Alvarez, who won the Nobel Prize, and he said, "Look what I found. I mean, this just shows special relativity is just wrong, and we know why." And you know what he said? He says, "I'm too old to fight. I've been around." And I think a lot of people will do this. It's like, I'm aware of it, I know, but this will change everything, and I don't want to do that right now. I just want to go to the beach, teach my plate tectonics, paint, that's my hobby, and go on. But I think the future of expansion tectonics is real. Here's my answer. It isn't just geology. It changes so many more fields. That's physics. It changed physics. It changes paleontology. Now, all of a sudden, everybody who's dealing with dinosaurs, you have a whole new area we should be forming PhDs and talking about paleogravity. We should be looking for evidence on paleogravity.
Here's a reason why there's dinosaurs in Western United States and Queensland, in Victoria, in Australia, is because they were right next to each other. When the dinosaurs were in existence, they just wandered across the countryside and got there. That's why there's the same dinosaurs in the United States as in Australia, for example. So it's just a way of looking at the data.
Yeah, it's going to change everything. Okay, well, listen, we got to go. I do have an idea. I just want to hold this for you. I put into the idea of making a Google Earth where you could change the radius with time. So you would put in a time and you could plot stuff on that at that way, and then actually have sort of things move. So if you make an area, you can do that. Well, obviously that needs to be programmed. To get people to do that is time. One of the ways these things can be done, and this is talking to everyone out there, one of my ideas is do a Patreon or not a Patreon, a GoFundMe project. And what happens is we have programmers all around the world. They can do this. All we would have to do is get enough people to put enough money together and have people start open sourcing programming this. This has been done before. It just, we would just get everybody throws in $50, $100 if they can. And what happens is you start paying people who charge $20 an hour to program, and they know how to program. So there is a way to do this and to do that. And I want to put that in your head. So we want to talk about that maybe another time. But thank you so much again for taking the time and to come on our show. I do think you should also start your own YouTube channel. Let's talk about that offline, because I think it's really important. You can, and you want to go as many places as you can, because that just increases the, how do you say, all the places they're going to find you and your work. So thank you so much for coming on.
You're welcome.
Okay. All right. We're going to take him, let him go to bed. It's now the next day in Perth, Australia. I really want to thank everybody who's been watching this. If you don't know expansion tectonics, you need to. It changes everything. Don't believe me, as I say, but check it out. Let's take ourselves out here. You want to stay tuned. Next week, we're going to show you why quantum mechanics is throw it out. It fails. That will be with Eric Reeder. You don't want to miss that. And as I always say, stay critical, stay thinking. I am Dave D. Hilster. I am your science therapist, trying to get you to the promised land of becoming a critical thinker and thinking on your own. Ciao for now.